Okay, now let's talk about the LU decomposition, because Gaussian elimination is not computationally very efficient, and since we need to do many row operations, perhaps we can simplify the Gaussian elimination if we can factorize our coefficient matrix so that we get some lower and upper triangular matrices from this factorization. So this will speed up our computation, because we will not need to do the row operations like in Gaussian elimination in order to get upper triangular matrix. So if you check Matlab, there is a function LU, and this is for the LU matrix factorization. And in simple form, you can see if you apply LU with a coefficient matrix A, it returns to you the lower and upper triangular matrices L and U, and it also produces this permutation matrix such that L times U is equal to P times A. Okay, and similarly we have in our lecture notes, we have the same notation, this L times U, which is what we obtain as the lower and upper triangular matrices from the factorization, is equal to the P times A. So basically you might wonder, so how does it really make the Gaussian elimination more efficient? Basically we can split the problem into two steps, because notice that if you multiply the original problem AX times Y, AX equals to Y, if you multiply both sides by the permutation matrix P, right? So what you'd get is PAX on the left hand side, and the right hand side you have P times Y, okay? But notice that P times A, if you apply the LU decomposition, is written as L times U. So this means actually we have a two-step problem. So we have two systems of linear equations actually. The inner problem, U times X, we can let this equal to Z. So this is one system of linear equations. And then once we obtain this Z, we can solve the other system, which is L times Z equals to P times Y. And notice that P times Y is a vector, that's the right hand side. And you have this L, which is a matrix, times the variables Z, which you are looking for. So first you need to solve for Z. Okay, so you can solve for Z by L times Z equals to P times Y. So we can use the Gaussian elimination here to get this Z. And then once we get Z, now we can use this to solve for X. Right? Remember, we have Ux equals to Z as the second system of linear equations. And here we can get our solution which we are looking for, which is the solution of X. Okay, so these two can be combined as a single line. So basically we are doing two Gaussian eliminations here to get the solution. So what's the efficiency gain here? Notice that this L and U are much easier to solve because these are already lower and upper triangular matrices. In other words, to solve these by the Gaussian elimination, we don't really need row operations, because this is already at the form that we would like to see. So let's see a Matlab example and we can apply this quickly. So you have a given coefficient matrix for a system of linear equations, and basically let's type this quickly, and this is my coefficient matrix A. So if I if I want to factorize this matrix, then I just use this LU function in Matlab, and you can see it will produce me all the things that are needed to solve this system efficiently. So how can we get a solution if we are given the right hand side? So suppose our right hand side is given as this y, 12 and minus 20. So that's my right hand side of the system of linear equations. So here you can see that we have several alternative methods to use. So one thing we can do is let's say the direct inversion, because if we take the inverse and multiply both sides of our system of linear equations, we can get the solution, obviously. So that's going to give us one possible way. But matrix inversion is computationally not very efficient, so we will usually not prefer, especially if our coefficient matrix A is a large matrix. This computation will be quite slow. So this is not our preferred method of solving this system. However, we can use it to verify our solution. And we can also use the Gaussian elimination directly using the backslash operator. You can see we get the same answer. And now let's use our LU decomposition method. And notice that we will apply the Gaussian elimination twice. And we have this P times Y. So we can see that LU decomposition method also gives us the same result. But as we can see, especially for larger problems, obviously, LU decomposition method should be our first choice. It's going to be the most efficient one out of what we have seen here.